we'll discuss about registers. So let us see what is a register basically. A register is a memory element which is mainly used for holding multiple bits of information. As we have seen, one of the memory element, that is flip-flop, which is basically used for holding one bit of information, either 0 or 1. Now here register is again a memory element which is going to hold multiple bits of information, and these registers are mainly designed with the help of D flip-flops. Okay, so if I want to design a 4-bit register or n-bit register, then I would require a total number of n flip-flops. Okay, so let us see that. So an n-bit register has a group of n flip-flops and some logic gates and is capable of storing n bits of information. So if you want to design an n-bit register, then definitely you need to use n flip-flops. Okay, now the flip-flops store the information while the gates control when and how new information is transferred into the register. So here flip-flops are used for storing the information, and we'll also use gates along with these flip-flops for controlling the data inputs. Okay, that means when we want to load the new input inside the register or else the flip-flops. Okay, now let us see some of the functions of the register, that is retrieve data from register, store or load new data into the register, that is done parallelly and serially, and we can also shift the data within the register towards left or else towards right. Okay, now let us see all these functionalities of this register. Now let us see a simple register which is designed with the help of D flip-flops, and it is a 4-bit register. So as I told you that if I want to design a 4-bit register, then definitely I require 4 flip-flops. As you can see, 4 flip-flops, and all these flip-flops are given with a same clock pulse, so these are called as synchronous flip-flops. Okay, and now this clock pulse is a positive edge triggered clock pulse, therefore each and every D flip-flop would be responding only to the positive edge of the clock pulse. Okay, now here I0 to I3 are the inputs which are connected to the D inputs of the flip-flops, and A0 to A3 are the outputs. Okay, as you can see here, for every positive edge of this clock pulse, now these flip-flops would be processing the inputs and then it would be producing the outputs. Okay, so here for every clock pulse, even if we are not changing the inputs, for example, assume that initially my input is 1 1 0 0. Okay, now during the first positive edge of this clock pulse, these flip-flops would be processing the inputs and would be producing the same outputs. As you know, what is the functionality of the D flip-flops. Okay, now during the second clock pulse, or is during the second rising edge of this clock pulse, okay, assuming that I'm not changing the input, okay, then even though these flip-flops will be processing the inputs and again producing the outputs. Okay, so this data processing of the inputs will be controlled with the help of gates. Okay, so let us see how to do that. So registers with parallel load, those are called as parallel load. Why? Because we are giving the input parallelly. Instead of loading the register at every clock pulse, we may want to control when to load. Okay, loading a register, which is nothing but transferring new information into a register, requires a load control input. Okay, so loading is register is nothing but storing some new information into the register, and in order to store the new information, we require a load control input. Okay, and parallel loading is nothing but loading all the bits simultaneously or at a time, is nothing but parallel loading. Okay, now let us see all these terms with the design. Okay, so register with parallel load, as you can see here, 4 flip-flops are used for designing the 4-bit register, and then some gates are used here. These are the gates which are going to control the data inputs when actually they should be loaded into the flip-flops. Okay, and A0 to A3 are the outputs, and as you can see, these gates are receiving the inputs from load and then the original inputs, that is I0 to I3, as well as they are receiving the input from the outputs as a feedback element. Okay, so whenever this load input is 1, then the new data will be loaded into the flip-flops. If this load input is 0, then these flip-flops are going to retain the previous state. Okay, let us see that with an example. Assuming that initially now these flip-flops are holding 1 1 0 0. Okay, now these flip-flops are holding 1 1 0 0. Okay, now assuming that load input is 0. So as load input is 0, then the output of this inverter would become 1 and this inverter would become 0. Okay, now as this inverter output is 1, Therefore, the output of this AND gate now would be depending on A0. As A0 is 1, therefore the output here would be 1. And as one of the input to this AND gate is 0, so whatever the thing that you apply at this I0 will not be processed out. Therefore, the output would be 0. Now, the inputs to this OR gate, one is 0 and the other is 1. Therefore, again the output of this OR gate would be 1. Now, this 1 would be processing by this flip-flop. Therefore, the output that we are going to get here is again a logic 1. Okay, so here as load input is 0, now this flip-flop is retaining the previous state. Okay, this is similar for all these flip-flops. Okay, now assuming that if load input is 1 and this I0 input is 0. Okay, load input is 1 and I0 input is 0. Now let us see what happens. As this load input is 1, now the output of this NOT gate would be 0 and the output of this NOT gate would be 1. Okay, now as one of the input of this AND gate is 0, therefore the output will not depends on the A0 input. Okay, therefore the output would become 0. Okay, now here this load input to this AND gate is 1. Okay, so it would be waiting for the next input. Now here the next input, that is the original input, is 0, therefore, or else I0, now this I0 would be processed out, that is 0. Okay, now 0 as well as 0 to the inputs of this OR gate, the output of this OR gate would be 0 and this 0 will be processed by the D flip-flop and then you'll be getting the output as 0. Okay, so this is how a new data is loaded into the flip-flops or register with the help of a control input, and that control input is called as load. Okay, so this is how we are going to load the data parallelly, that is new input parallelly, and we can also retain the data without or by giving a logic 0 at this loading. Okay, now let us see the other feature of this register, that is shift registers. Okay, we can use them for shifting the data. Another function of a register besides storage is to provide for data movements. So we are going to use registers basically for storing the information, and we can also do the data movements. That is nothing but we can also move the data towards right or towards left with the help of these registers, and that is called as shift register. Okay, and each stage in a shift register represents one bit of storage, which is nothing but a flip-flop, and the shifting capability of a register permits the movement of data from stage to stage within the register or into or out of the register upon application of clock pulses. So as soon as we give the clock pulses, therefore the data which is present inside the flip-flops will be shifted towards right or else towards left. Okay, so that is the data would be shifted from one stage to the other stage. So here stage is nothing but a single flip-flop. Okay, now let us see that design. Basic data movement in shift registers. 4 bits are used for illustration. So here we are using only 4-bit registers. So as I'm using only 4-bit register, therefore how many flip-flops we require? A total of 4 flip-flops. Okay. Now here the first basic functionality that we can go with serial in, serial out. Okay, or else we can also call it as shift right register. Okay, as you can see, the data is given serially and the data is taken at the output as serially. Okay, so serial is nothing but giving the data in bit by bit manner, and parallel is nothing but giving the data or giving multiple data at the same or simultaneously. Okay, so here one more functionality, that is serial in, serial out, but this can also be called as shift left register. Okay, as you can see, the data is in from the left side, okay, sorry, from the right side, and the data is out from the left side. Okay, and the other functionality is parallel in, serial out. As you can see, the data is entering parallelly, that is all the data inputs are given simultaneously and data is shifted out serially. So that is what is called as parallel in, serial out. Okay, and the next is serial in, parallel out, where the data is in serially and the data is out parallelly, that is multiple bits are out at the same time or simultaneously. Okay, and then parallel in, parallel out, where you can see all the data bits are in parallelly, that is simultaneously, and data bits are out simultaneously. Okay, and one more functionality is rotate right. As you can see here, this data is moved towards right side, and this LSB is again copied into the MSB. Okay, but in some other cases here this LSB is shifted out, which is nothing but it is something like discarding the output. Okay, and rotate left, where you can see the data is moving towards left side, and this MSB is again copied into the LSB of the same register. Okay, now let us see all these designs with the help of flip-flops. So initially we'll go with serial in, serial out shift register. So it would be accepting the data serially, 1 bit at a time, as we know that, and also produces output serially. Okay, so here the same clock is given to all these flip-flops, therefore it is these are called as synchronous flip-flops. Okay, and serial data in to this D flip-flop, and the outputs is Q0, Q1, Q2 and Q3. So here Q3 is the MSB. Okay, now let us take an example here, assuming that our data input is 1100. Okay, 1100, therefore 1 is the MSB and 0 is the LSB. So initially I am giving the input from the MSB. Okay, so here the input is 1, and during the first rising edge of this clock pulse, okay, now this all the flip-flops will be processing their inputs. Okay, now the inputs for the remaining flip-flops, these flip-flops are zeros, but whereas coming to the first flip-flop is 1. Therefore this input is processed and it would be producing the output as 1. Okay, here Q0 is 1, Q1 is 0, Q2 is 0 and Q3 is 0. Okay, now during the second rising edge I am giving the input again as 1. Okay, now this flip-flop would be processing this one, and the output, that is Q0, okay, in the early stage or previous stage is 1. Now that is processed by this second flip-flop. Therefore during the second rising edge, okay, now the output of this flip-flop would become 1, and the output of this flip-flop would become 1, and this becomes 0, and Q3 also becomes 0. Okay, and during the third rising edge, if I am giving the input as 0, now this 0 is processed by this first flip-flop, and Q0 is initially 1 now in the earlier stage, therefore that 1 is processed by this flip-flop, and Q1 was 1, therefore that is processed by this flip-flop, and Q2 was 0, then that is processed by this third flip-flop or fourth flip-flop, therefore the output Q3 now is 0. Okay, and last input 0, therefore now the output here would become 1. So output Q3 would become 1, Q2 is also 1, and then Q1 is 0 and Q0 is 0. So this is how we are going to shift the data serially from the input towards the output. Okay, now this is done, this is shifting towards right. We can also implement the same, that is shifting towards left, that is giving the data serially from this side and then taking the data serially from the left side. Okay, now let us see one of the application of this serial in, serial out register, that is serial transfer of data from one register to the another register. Here our intention is to shift the data serially from one register to the other register. As you can see, there is an AND gate whose inputs are clock and shift. Okay, now if this shift control input is 1, then only these registers are going to receive the clock input. So if they receive the clock input, then only they can shift the data towards right side. Okay, so assuming that this shift control is 1, and initially shift register A as well as shift register B is holding some data value. Okay, now during the first clock pulse, now the LSB of this shift register A would be shifted out, and that is copied into the MSB of the same register as well as shifted into the shift register B. Okay, for the first clock pulse 1 LSB, and for the second clock pulse the next bit, third clock pulse third bit, and for the fourth clock pulse the next bit. So this is how we are going to transfer or shift the data serial. Okay, let us see this with an example. Here initial value of shift register A is and B is given here. Okay, that is 1011 and 0010. Now after T1, what happens here is this value is copied into the MSB, okay, and the same value is shifted into the shift register B. Therefore the value, that is the LSB of this shift register B will be loaded outside, or it would be discarded. Okay, so this is how the shifting operation takes place in case of serial in, serial out shift register. Okay, so let us see the next one, that is serial in, parallel out shift register. Okay, so here it accepts the data serially and outputs the data parallelly, which is nothing but simultaneously. Okay, again the 4 flip-flops are taken here, that is in order to make or in order to design a 4-bit register, and all the flip-flops are going to receive the positive edge triggered clock, that is synchronous clock. Okay, and data in is given to the first flip-flop, and the output of this first flip-flop is given as an input to the second, and the output of this is given as an input to the next. Okay, and here the output is taken parallelly, that is individually at each and every output of the flip-flop. Okay, so assuming one more example here, like 1100, here again Q3 is MSB. Okay, so initially I am giving the input as 1. So during the first rising edge of this clock, all the flip-flops are going to process the inputs. Now the input which is present to the remaining flip-flops, that is these 3 flip-flops, would be zeros, but whereas the input that is available for this flip-flop is 1. So during the first rising edge of this clock, now this would be processing the input, therefore the output would become 1, but whereas the output at Q1, Q2 and Q3 is zeros. Okay, now I am giving the next data input, that is 1, therefore this 1 is processed by this flip-flop, and 1 which is present at this Q in the earlier stage that we got as output, that is processed by this flip-flop. Therefore during the second rising edge, now this 1 is processed by this, and the 1 which is present at the Q0, that is processed by the second flip-flop. Therefore the output at Q1 and Q0 would be 1 and 1. Okay, and the third input that I am going to give is 0. Now this is processed by the first flip-flop, therefore the output at Q0 would be 0, and Q1 would be 1 and Q2 would be 1. Now during the fourth rising edge, if I am giving the input as 0, then the output would be 0 at Q0, 0 at Q1, and Q2 and Q3 would be 1s. So this is how we are going to shift the data parallelly. Okay, this is serial in, parallel out. As you can see, in this way we can represent with a block diagram of this serial in, parallel out. There you can see one data input, a clock input, and then 4 outputs. Now let us see the next functionality, that is parallel in, serial out. Parallel in is nothing but giving the data in simultaneously or at a time, and then taking the data serially outside, that is bit by bit at the output. Okay, so for giving the data parallelly, here I am using some gates for controlling the loading of these inputs. Okay, now here if this shift bit is 1, therefore the data would be shifted outside, that is towards right, and if this control input is 0, then the data or new data will be loaded into the flip-flops. Okay, now let us assume initially the D3, D2, D1 and D0 are 1, 1, 0 and 0. Okay, now let us see what happens. Assuming that this input is 0, as this input is 0, therefore the output of this NOT gate is 1. Now that is connected to this AND gate, and the output of this, that is 0, which is connected to this AND gate. Okay, so as you can see here, D0 is loaded directly and D1 is loaded. Why? Because as the input of this AND gate is 0, therefore the output is 0, and here input to this AND gate is 1, therefore whatever the value that is present on D1 would be the output of this AND gate, and that is given along with this output as an input to this OR gate, and this output is connected to the second flip-flop. Okay, so in the same way D2 will be loaded here to the third, and D3 will be loaded into the fourth flip-flop. So this is how the loading takes place with the help of this control input. Okay, and if this control input is 1, then the shifting operation takes place. There you can see for the first rising edge, Q is 1. Now that Q is 1 here given to this AND gate. Okay, and Q1 is 0, and here Q0 is 0. Okay, now here the output of this AND gate would be Q2, and that Q2 would be given at this D input, and here it is Q1 and that is given to this D input, and here it is Q0 that is given to this D input. Okay, so this is how the data is shifted towards right side or shifted serially outside. Now this is the block diagram where I am going to represent the control input along with the clock, and then parallel data in along with serial data out. Now let us see the last functionality, that is parallel in, parallel out shift register. Okay, now here the data is given parallelly. As you can see, D0, D1, D2 and D3 are loaded parallelly at same time, and they are taken parallelly at the output side, that is Q0, Q1, Q2 and Q3. So if I am giving 1, 1, 0, 0, so during the rising edge of the first clock, what happens? The same input would be processed, or the inputs would be processed by all these flip-flops, and then they will be producing the outputs independently. Okay. Now let us see one more functionality, that is bidirectional shift register. Now this is the bidirectional where we can shift the data towards right as well as towards left. Okay, serial data in from here and serial data out from here. Okay, as you can see, if this control input is 0, then the data would be shifted towards left. If this control input is 1, then the data would be shifted towards right. Okay. Now let us see one more application, that is serial addition, how to perform serial addition. So here there is one register shift register A and there is one more register shift register B. Assuming that both are holding some data, okay, and the outputs of these are connected to one full adder where the inputs are X, Y and then Z, which is nothing but the previous carry, and the outputs are sum and a carry. And here you can see some control inputs like shift right as well as the clock pulse. Okay, let us study this with an example. Okay, so whenever you're giving the shift input as well as the clock input, now the data, that is LSB of this shift register A as well as B, will be shifted out, and that is given as an input to the full adders along with the previous carry, as the previous carry initially would be 0, therefore it would be performing, the full adder would be performing the addition between X, Y as well as Z and producing the output as S and C. Okay, and this S is again copied into the MSB of the shift register A. Okay, here our intention is to perform A plus B, and the result should be written into A. So that is why we are copying this S result into the shift register A. Okay, let us study this with an example. So here, assuming that A is holding 0100 and B is holding 0111, so the result that we have to get is 1011, and it should be stored inside the A, and this is going to happen only after 4 clock pulses. Okay, now let us see what happens during the first clock. So initially this is the data that is present, that is Q is 0 and A holding this value and B is holding this value, and during the first clock pulse what happens here is this data 0, 1 as well as this Q would be added, 0 plus 1 plus 0, and here we are going to get the sum as 1 as well as the carry as 0. Okay, and so here Q output is 0 and this sum is copied into the MSB of the A register. And during the second clock pulse what happens here is this 1 as well as 0 is added along with the Q. So here you can see 0 plus 1 plus 0 and sum is 1 and carry is 0. Now this sum is copied into the MSB of the register A. Okay, and now Q is here 0. And during third clock pulse these two ones are added along with Q0, therefore sum is 0 and carry is 1, and this sum is again copied into the MSB of the shift register A, and the output now here is 1, that is the carry is 1. Now during the fourth clock pulse 0 and 0 gets added along with 1, therefore sum is 1 and carry is 0, and this sum is again copied into A and Q is now 0, and this is what the final result which we are going to get. And this is how we can use shift register for performing the addition between two registers or two operands. Now let us see shift register counters. We can also design counters with the help of these shift registers. Those are called as shift register counters, and there are mainly two types of shift register counters. They are ring counter as well as a Johnson counter. Okay, a shift register with serial output connected back to the serial input. Okay, so shift register counter is nothing but connecting the output of the shift register as a serial input, that is as a feedback input. Okay, they are classified into two types, as just now I said, ring counter as well as the Johnson counter. So initially we'll see what is this ring counter first. So ring counter, one flip-flop for each state in the sequence. The output of the last stage is connected to the D input of the first stage. So here we have to connect the output of the last stage to the D input of the first stage, and an n-bit ring counter cycles through n states. So if you are taking a 4-bit ring counter, then the desired output state that we are going to get is 4 states. Okay, no decoding gates are required, as there is an output that corresponds to every state the counter is in. Okay, now let us see the design of this ring counter. So here I am taking a 6-bit register, therefore 6 flip-flops are required, and this is a 6-bit ring counter. The output of the last stage is connected as an input to the first stage. Okay, now assuming that the initial state of this ring counter is 1, 5 zeros. Okay, and during the first clock pulse, what happens here is the data would be shifted out by this D, as well as all the flip-flops would be shifting the data whatever they are holding towards the outside. Okay, that means now this Q0 will be shifted towards Q1, and Q1 will be shifted towards Q2, Q2 to Q3, Q3 to Q4, and Q4 to Q5, and Q5 would be copied or else would be loaded into the first D input. Okay, so this is how for every clock pulse the data will be shifted towards outside. So that means here we are going to get a total of 6 states. Okay, now after 6 states, again it is going to get the initial state, that is 150. So that is why it is called as a ring counter. Okay, so for designing an n bit ring counter, we require n flip-flops. Okay, now let us see the next one, that is Johnson counter. So here the complement of the output of the last stage is connected back to the D input of the first stage. So we are connecting the complement, which is nothing but Q0 bar or Q bar of the last stage as an input to the D input of the first stage. Also called the twisted ring counter, require fewer flip-flops than ring counters but more flip-flops than binary counters. An n-bit ring counter cycles through 2n states. Okay, so if it is a 4-bit ring counter, then it will be producing output as 8 states. Okay, so this is what the advantage that is present with Johnson counter as compared with the ring counter, whereas ring counter will be producing only 4 states. Okay, require more decoding circuitry than ring counter but less than binary counter. So let us see the design. So here it is a 4-bit Johnson counter. Okay, and the output states that we are going to get is a total of 8 states. Okay, initially assuming that all these flip-flops are loaded with the initial value, that is 0. Now during the first clock, what happens here is Q0, that is Q0 would be shifted towards right, Q1 again right, and Q2 is again right, and Q3 is shifted towards the right side, but Q3 bar is copied or else is loaded as an input to the first state, that is nothing but 1. Okay, so for every clock pulse, these inputs are shifted towards right, as well as Q3 bar is given as an input to the first D flip flop. Okay, so after 8 states, that is from 0th to 7th, which is nothing but 8 states, during the 8th clock pulse or 9th clock pulse, it would be initialized, or it would be getting the initial state, that is 4 zeros. Okay, so this is how we are going to design the Johnson counter with the help of D flip-flops. Okay, so in the next session we'll discuss about ripple counters.